Okay, so the title of my 3 lectures is the unitary Fermi gas, relations, symmetries, and diagrams. So this will be basically lecture 1, 2, and 3. And well, in fact, I put here the unitary Fermi gas because it's the most important situation. But in fact, only this part will be really about the unitary limit, infinite scattering length. And this first and the last part will be more general, so it will be arbitrary scattering length. And therefore, if you want, you can replace unitary here by resonant. So resonant meaning that we have large scattering lengths compared to the range, but it doesn't need to be infinite. And this thing is already bothering me. Okay, so so I divide it into chapters. So the first chapter is about the concept of resonant interactions. So there will be some overlap with Yoke-Waller-Raven's lecture, but I think I will have a bit different point of view, and the universal zero-range limit. So by the way, I will scan my handwritten notes, which are maybe the handwriting is slightly better than on the board. First, let me start by discussing the two-body problem. So let's consider two distinguishable particles. So in fact, for now, just assume that they are distinguishable, but of course, later on, this will correspond to, in fact, two different spin states, spin up and spin down of our Fermi gas. But the point here is that the wave function psi of R1, R2 has no symmetry constraint when we exchange R1 and R2, because they are distinguishable particles. So, just to warm up a bit, even though the heating is already too much, but okay. Let's write down the two-body Schrödinger equation, minus h bar 2 over 2m times Laplacian with respect to R1 plus Laplacian with respect to R2 psi. And then we have some interaction V of R between the two particles times psi equal to E psi. Of course, what I call R here, it's the distance between the two particles. So it's the norm of the vector R, where the vector R is R2 minus R1. Now, of course, you want to introduce the center of mass, C, which is R1 plus R2 over 2. And then, of course, you in this problem, you have a separability of the center of mass, meaning that the wave function psi of R1, R2 is a product. I mean, all the eigenstates can be written as a product psi Cm of C, center of mass wave function, times the psi internal, psi int of R. So R is the relative position. And of course, this is because this sum of kinetic energies can be written as center of mass kinetic energy plus relative kinetic energy. and also because this potential here depends only on the relative position. After doing that, and in the following I will call this guy just psi. I will drop this subscript internal. Then you get, of course, Schrödinger equation just for the relative motion, so minus h bar squared over m, Laplacian with respect to r, psi plus v of r, psi equal to e psi. Now, in fact, this should be the internal energy, but I will drop this subscript. So just for definiteness, I will consider the following interaction potential. So my favorite V of R, it will be a square well, but actually I will also add a repulsive hardcore for reasons that I will explain later. So that so here I will call this B over 2 and this also B over 2. So just a simple concrete potential. And the width, the depth of this potential, it will be convenient to write it as little v0 times some convenient factors, namely h bar squared over mb squared. So b, I remind you, is the range of this potential, times pi squared. And you will see in a minute why this is a convenient choice. So now let's look at the bound states in this potential, in other words, the dimers, or diatomic molecules. So in other words, let's look at the solutions of the Schrödinger equation at negative energy, where of course then this wave function is normalizable. So as a function of the this depth parameter v0, what happens, because we are in 3 dimensions, is that when v0 is very small, there is no bound state, and then there is a critical value where the first bound state appears, and because I put these convenient factors here, this critical value is 1. So you get a bound state that appears, and the energy will do something like that. And then it will go further down, and I will use another color just to say that in the beginning, just after this bound state appeared, it's actually weakly bound. So weakly bound in the sense that the binding energy is small compared to the depth of the potential, which is on the order of h bar squared over mb squared. So that's a weakly bound dimer, and correspondingly the size of this dimer is much bigger than the range B. And on the other hand, once we increase the depth of the potential beyond this critical value 1, significantly beyond, then this condition is not valid anymore, and then we get so-called deeply bound dimer. Meaning that now the binding energy is on the order of the depth of the potential, h bar squared over mb squared. And the size of the dimer will be on the order of b. Now we can also look what happens if you continue to increase this depth. At some point, of course, there will be another dimer that appears, and again in the beginning it will be weakly bound, and then it will become deeply bound. Okay, so that's it for the dimers, and now let's look at the scattering states. is the second dimer. And then, of course, there are more of them if you continue to increase V0. So for the scattering states, namely the positive energy solutions of this Schrödinger equation, in fact, as you know, you need to specify some boundary condition at infinity. So for this, you write the energy as h bar squared k squared over m, and then you impose the standard behavior for your wave function at large r, and namely it should be an incoming plane wave e to the I k dot r plus outgoing wave, which is usually written fk of r hat, I will explain it in a second, times e to the ikr over r. And this thing is called the scattering amplitude, and r hat stands for the unit vector r divided by the norm of r. So in general, the scattering amplitude depends on the direction. But if we take the limit of zero energy, k going to 0, then as you learned from Yoke, this scattering amplitude fk of r actually becomes independent of the direction. So you only have S wave scattering, and this limit by definition it's called the minus the scattering length. I'm missing a minus here, so I should correct before I put it online. So now the interesting story for us is that there is universality here. And this universality happens, for example, if we are here where we have this weakly bound dimer. So if we are if we consider the limit where V0 is slightly above 1, V0 goes to 1 plus, then what happens is that the scattering length divided by the range B goes to plus infinity, and the binding the energy of the dimer goes like minus h bar squared over ma squared. And by the way, so I will use the notation equivalent in the mathematical sense. So in the sense that f divided by g, g tends to 1. So this does not mean it's on the order of, but it really means that it's equivalent and there is no missing prefactor. So so this is a first example of universality in the sense that actually this holds for any shape of the potential here. So you can take, for example, a Lennard-Jones potential, which would be more realistic. And again, you go to the limit where you have a dimer which is weakly bound, which is just appeared, and this law will be valid in the limit of a very weakly bound dimer. Also, the wave function has a universal behavior, namely in this limit, which is called the resonant limit, by the way. The wave function will approach the following universal form. So there is a normalization factor, and then it's e to the minus r over a divided by r. Okay, so these are our first examples of universal results. Another slightly more convenient way to view this story is to consider the zero range limit. Namely, instead of fixing B and tuning the depth as we have done here, we will rather send the range, the width of the potential B to 0. So that's why it's called zero range limit. And we should keep the scattering length fixed. And to achieve this, it's easy to see that actually we should once again send V0, this depth, dimensionless depth of the potential, to 1. But now it will depend, the way how we have to send it to 1 will depend on the scattering length that we want. So it looks as follows. So V0 as a function of B. So first, if A is positive, then we are back to the situation that we already discussed here. So if A is positive, then you have to send V to 1 from above, like here. Now, another interesting situation is when A is infinite. And in this case, you will just have to keep V0 equal to 1. And the reason is quite clear. So you see that when V0 is exactly 1, that's the situation where you have your dimer, which is at 0 energy. If you want, the dimer is just not existing anymore. And in this case, the scattering length is infinite. So that's what you need to do in order to do the zero range limit with infinite scattering length. So you see that your depth here should just be this given by this expression. So you have to scale the depth like 1 over b squared. So note that this is a different than a Dirac delta. For a Dirac delta, you should have the depth like 1 over b cubed in 3D. So you see that this is different from a Dirac delta. And then finally, of course, we also want to do sometimes a negative scattering length. And in this case, well, you need to do this. So you need to have V0 approaching 1 from below. So yes. I will come back to this later. Yeah. So for the time being, let's just consider that we look here. But I will come back to what happens if we are here, for example, later. Because, of course, in experiments, we are rather here. Or, in fact, we are even at the number 20, dimer number 20 or so. OK, so you see that's quite natural. If you want to have a positive scattering length, then you have to make your potential slightly deeper than 1, so that you just have a weakly bound state. And if you want to have a negative scattering length, then you should make your potential slightly less deep, so that you don't have a bound state at all. But still, you almost have a bound state, so that the scattering length is large in absolute value. OK. So So there is one interesting situation to consider apart from the strictly negative energy and strictly positive energy. It's also interesting to look at energy exactly equal to 0. And then, so we have to solve the Schrödinger equation now with 0 in the right-hand side. And So therefore, you see that if R is bigger than the range B, we just have to solve a Laplacian of psi equal to 0. So for this particular situation of zero energy, I will the wave function I will denote it by phi 0. So it should have a Laplacian equal to 0. And therefore, if we exclude some unphysical behavior, phi 0 of R should be a linear combination of 1 over R and a constant. And so if we take here 1 over R, so this will fix the normalization of our wave function. Of course, it's not a square integrable, but we can fix the normalization by saying that this constant here is 1. And then it turns out that this constant here will actually be minus 1 over the scattering length. And that's quite easy to see if you start from the scattering state here, and then you take the limit k going to 0, and you replace, so here you get 1, and here you get minus a times 1 over R. So this is indeed this one up to a normalization factor which is different in this case and in this case. So so this is something that we will use later at some point. So now let me turn to the zero range model, which will be very important for us. And I will denote it by ZRM in the following. So the idea of the zero range model is the following. We see that if we take some finite range model, like for example this one, and then we send the range to 0 with a fixed scattering length, we get some universal results such as these ones. And in fact, the zero range model, it will allow us to directly get these universal results without taking first the finite range and then sending it to 0. So it will be much more convenient. So the zero range model is defined as follows. When so I'm still now talking about the two-body problem. So when the relative position R is different from 0, then we should just have the Schrödinger equation minus h bar squared over m Laplacian psi, but without any interaction, because now we are immediately outside of the range of the interaction, because the range is 0. So there is no interaction term here, and this is just equal to e psi. So of course, if we would stop here, then we would have no interaction at all, which is not what we want. So in fact, in order to have the interaction, what we need to do is to impose a boundary condition when R goes to 0. And this boundary condition looks as follows. It says that the wave function psi of R, when R goes to 0, it should behave like 1 over R minus 1 over A. So it's not a coincidence that it's this thing, times some constant, capital A, and plus higher order terms, so plus a term of order R. And this boundary condition is very important, and I will call it a contact condition, because it concerns what happens when two particles approach each other, get into contact, and for short I will denote it by CC. So that's the zero range model for two particles. So note that, as I mentioned before, we cannot use a Dirac delta in 3D, and that's why we have to use these boundary conditions. In 1D, actually, the zero range limit does correspond to the Dirac delta, and then in 1D you can write just here Dirac delta of R or of X, since you are in 1D. But in 3D this is not possible, and in 2D it's not possible either. So now let's consider this zero range model, and what you can now very easily find is that there is one dimer when the scattering length A is positive, if A is positive, and the energy of the dimer, as I already announced, is just exactly given by this universal formula. And the wave function of the dimer is just exactly given by this form. And now you can obtain this in the zero range model extremely easily, just by solving this equation with this boundary condition. Well, here it's a bit more tedious because you would first need to solve with this potential and then take the limit. Also, if you look at the scattering states for the zero range model, you can easily find that actually the wave function is just equal to, for any R, equal to this thing, and the scattering amplitude is equal to minus 1 over R A plus IK. And if you take A equal to infinity, then you maximize the modulus of the scattering amplitude, and you reach the unitary limit, which is the maximum value allowed by the optical theorem. So that's why it's called unitary limit. And that's it for the two-body problem. Any questions? Yep. I mean that this holds not only for this particular potential, but it holds for pretty much any reasonable shape of the potential. Reasonable meaning that it should decay sufficiently quickly at infinity. And of course, what's most interesting for you is that it also holds in the experiments. I will come back to that a bit in more details later. Any other questions? Yeah? It means that it's a term which is of order R. It's bounded by R times a constant. So it's just a higher order term. This is the leading order. There is a divergence, then there is a constant, and then of course there are other terms which go to 0. Okay, so now after these preliminaries, let's switch to part 2, which is the n-body problem. So now our wave function psi depends on R1, R2, up to Rn. And of course, we will consider fermions following the topic of the school with two internal states, which experimentally they are hyperfine states, but we will just denote them by spin up and spin down. And as I already mentioned, in fact, it's convenient to imagine that these are just two distinguishable types of particles. So in fact, you can, for most practical purpose, you can forget about the fact that this is one and the same atom in two different hyperfine states, because in most experiments the atoms will never flip the spin. They will never change the internal state. So therefore you can imagine that they are just two different types of atoms, say the red atoms and the blue atoms, and red and blue are distinguishable. Of course blue and blue are indistinguishable, and red also. So therefore we can consider that the number of spin-up atoms and the number of spin-down atoms are fixed. Of course the total number is n up plus n down. And our many-body wave function here, it should be anti-symmetric only if we exchange two particles of the same spin. So for example, if I put all the spin-up particles first, so I say that these R1 up to Rn up are the spin-up particles, and then from n1 plus 1 to the end Rn, these are my spin-down particles, then the wave function should be anti-symmetric if I exchange two of these guys. So if I exchange them, the wave function should change sign. And same story if I exchange two of these spin-down guys. But there is no symmetry constraint here. Actually, yeah, if you exchange a spin-up with a spin-down, nothing special should happen. Okay? So now let me write down the zero range model for this n-body problem. So of course it will be very similar to the two-body case. So first of all, there will be I'm just thinking. Actually, I will write it in some corner here because I will need it again later. So I'll try to put the zero range model up here. So first of all, if all the interparticle distances Rij are strictly positive, so meaning that you don't have two particles at the same point, then again you will have just the Schrödinger equation without any interaction term. So meaning that you have minus h bar squared over 2m, and then sum over I from 1 to n, sum over all particles of Laplacian with respect to Ri, plus I will put an external potential as well, u of Ri, psi, equal to e psi. So psi here, of course, is a function of R1 up to Rn. So this external potential, you will see that it will be convenient actually in the tomorrow's lecture to consider that it's a harmonic trap, but you can also consider that it's a box and take the thermodynamic limit. This is actually what we will consider today. And then, of course, we need to write down the contact condition. So now, for any pair of particles, if Rij, the distance between particles I and j, goes to 0, the wave function should satisfy some boundary condition. Namely, it should be given by 1 over Rij minus 1 over the scattering length times some constant a, which depends on some stuff I will write down in a second, plus again a term of higher order, of order Rij. And so this is maybe slightly pedantic, but to be really accurate, we should specify that actually this constant here depends on the center of mass coordinate Cij. So here Cij is the center of mass of particles I and j, so it's Ri plus Rj over 2. And it will also depend, of course, on the positions of the other particles. So Rk, k different from I and j. And in fact, this limit here, Rij goes to 0, you have to take it while keeping all these guys fixed. Okay, so this is the contact condition in the n-body case. So again, this model is really correct because it's the limit. If you start from a finite range model and then you take the zero range limit, then this is the then you will get the zero range model. So so more precisely, I will not write this on the board now, but you will have it in the notes. But if you start from a finite range model again, for example this one, and then you write down the Schrödinger equation for the n-body problem with this potential. So it's just this equation, but now you will have also a term sum over ij v of rij psi. You will have the interaction between the particles. And then you take the zero range limit. So once again, b going to 0, the range going to 0, but keeping fixed the scattering length and also keeping fixed the external potential. Then what happens is that your finite range model converges to the zero range model. So for example, if you look at your spectrum, each energy will converge to an eigenenergy of the zero range model. And same story for the wave functions. For the eigenstates, each wave function will converge to a wave function of the zero range model. And again, you have universality in the sense that it holds for a broad class of potentials here. And now I will mention why I put a repulsive hard core here, because if you don't put it, then actually it turns out that for a sufficiently large number of particles, your ground state will be a collapsed state where your interparticle distance is on the order of the range B. And okay, I mean, this again, it's not really a big problem. In fact, in experiments, that's what happens. Your ground state, for example, for lithium, it's a solid. But here, then it makes the discussion slightly more complicated. So that's why I prefer to put a repulsive hardcore, which supposedly prevents this collapse. Okay, then I have some hand-waving justification of the fact that when you start from a zero-range model, indeed you get this boundary condition once your range is very small, once you go to the zero-range limit. And again, I will not write down absolutely everything. You can see it in the notes. But let me write down the main points. So if we start from the Schrödinger equation for a finite range potential, and now we do a change, we consider the situation where you have R and J, particles R and J, which are close to each other. Their distance is on the order of B. Let's say smaller than B, so somewhere inside the potential here. And then it's actually convenient to do a change of variable, exactly as we did in the beginning for the two-body problem. So you change variables from Ri, Rj to center of mass, Cij, and relative coordinate Rij. So this is Rj minus Ri. And then the Schrödinger equation can, in these new coordinates, it looks as follows. So you have minus h bar squared over m Laplacian with respect to Rij of psi. So psi here is now my many-body wave function. plus V of Rij psi. And then you have other terms. You have the kinetic energy corresponding to the center of mass, or Laplacian with respect to the center of mass. You have the kinetic energy from all the other particles other than I and j. And you also have the interactions between all the other particles equal to E psi. But now, remember, I consider a special configuration where these two particles are close to each other, while the other ones are far away compared to the range. Okay? Because here I'm trying to justify this boundary condition, where you have particles I and j which are close to each other, while the other ones are fixed. So now the point is the following. Since we are inside the range of the potential here, you see that this V of Rij here is pretty large, because remember we have this depth here, which is on the order of 1 over b squared, and b goes to 0. So that's really large. Okay, so this thing is large. It's on the order of 1 over b squared, and it's in fact it's negative. V is negative, so it's roughly speaking it's something negative on the order of 1 over b squared times psi. I'm dropping here the h bar squared over m. And now this thing here, you can easily convince yourself that it also has to be large, but now with a positive sign, 1 over b squared times psi. So the 1 over b squared is just because inside the range of the potential, the wave function will vary on a scale set by b. So for example, in this example here, the wave function has to vanish here. So it goes, as we are trying to derive here, it goes like 1 over r. And then once we enter the range of the potential, it has to quite quickly go to 0 here. So you see that within the potential here, the range of variation of the wave function is set by b. And therefore, once you take a spatial derivative Laplacian, you will get 1 over b squared, because this is second order derivative. On the other hand, all these other terms, they have no particular reason to be large when b is small. In fact, they should be just weakly dependent on b. And therefore, you see that these two guys have to compensate each other. There is no other way that to satisfy the Schrödinger equation than these two guys to compensate each other to leading order when b is small. Therefore, you see that basically this thing here to leading order should be equal to 0. And this is nothing else than the Schrödinger equation for the two-body problem, whose solution is actually phi 0 of r. So from this, it follows that psi of r1 rn is given to leading order when b is small by phi 0 of rij times some constant, which will depend as again on this other stuff. Voila, so that's my hand-waving justification of the zero range model. Because now we are almost there, because you see that if we now look at outside the range of the potential, then this will be just 1 over r minus 1 over a. 1 over rij, when rij is bigger than b. Okay, this is just this. Voila. So that's it for the first chapter. And please ask questions if anything is not clear. Okay, so in fact, indeed, it's not exactly 0, because there is this other stuff here, which is not exactly 0. But the point is that if I would here put an energy which is not 0, but say of order 1, then I will get either a scattering state or a bound state. But in any case, when r becomes small, because in the end we are interested in this limit when r is small, I mean larger than the range but still small compared to the rest, then actually you always get this behavior. So you can easily check it for the two-body problem. For example, if you take the dimer wave functions that I wrote down, you take r to be small compared to the scattering length, you get this behavior. I mean, in fact, this is already what the zero-range model is telling you for two particles, that you always have the same boundary condition. But you can explicitly check it for starting from a finite range. Yes? Yes? So yeah, C is fixed, and what goes to 0? No, it's fixed. So basically, I mean, it's just the natural thing to do. You have your two particles I and j, and you send them to each other while keeping fixed the center. Yeah. Other questions? Yeah. Not at all, no. I mean, of course, we are talking about instantaneous interactions from the beginning. For example, here it's already instantaneous, so I'm not discussing this point. But I mean, this is just it's just natural to do that because your interaction in the beginning, it only depends on the relative coordinate. So, but I mean, you see, I'm not telling you that this thing is obvious. I mean, this is what people figured out, and here I give you a hand-waving justification of it. But you know, it's not trivial at all to really prove that this is correct. And I will mention a bit about the mathematical results, rigorous results, tomorrow. Okay. So if you want, I mean, this zero-range model, you can consider it as a recipe, and as far as we know, this recipe is correct. Really mathematically correct. Okay, so now I move to chapter 2, which will be about tan relations. So these relations, by the way, were obtained by Tan in 2005 during his PhD. And he used some formalism of his own, which is people had a hard time to understand. And in the end, these papers were published only 3 years later. So if you have some good idea during your PhD, you know, and even if nobody understands it, maybe it's a good idea anyway. So okay, so here I will present things in a different way from Tan, hopefully in a very simple and clear way. And I will more or less follow some lecture notes, that are published in lecture notes in physics of Yvan Castin and me. And I will put the archive reference in the notes in case you want to take a look. And in some cases, I will also mention the paper that we wrote with Yvan Castin, so I also put the reference in the notes. But basically, all I will do here is to rederive these relations that Tan obtained. Just for simplicity, I will immediately consider the homogeneous gas in the thermodynamic limit. So in other words, I will consider the limit where we are in a box. We send the volume of the box to infinity. We also send the particle numbers n sigma to infinity. Sigma here is up or down. And of course, we should keep the density n sigma, little n sigma, which is big N sigma over volume, fixed. And also, we will consider a fixed temperature. So so we will work within the zero-range model. I mean, the relations are exact within the zero-range model, and for a given scattering length. And as I already mentioned, now here the scattering length can be anything. It doesn't need to be infinite. So these relations, they are about several quantities. So the first quantity is the momentum distribution n sigma of k. And since we are here in the thermodynamic limit, it's isotropic. And I will use calligraphic letters like calligraphic E to denote the energy per unit volume. And same story for the entropy. Calligraphic S is entropy per unit volume. Free energy per unit volume. P will be the pressure. Mu will be the chemical potential. So here, in general, we can have different chemical potentials for spin up and spin down if the gas is polarized. I will also denote by G2 of R the density correlation function. So it's expectation value of n up of R, n down of 0. So that tells you basically the probability to have two particles at distance r in your gas. And then these relations, they involve a new quantity, which is, I will denote by C, and this is called the contact, or Tan's contact. And again, I will use calligraphic C to be the contact divided by the volume, which is the intensive quantity. Because that's the interesting one, the most interesting one. But yeah, so the relations will involve this one. Okay, so the relations are the following. So the first one tells us that the momentum distribution n sigma of k at large k going to infinity, is equivalent to contact density over K4. So there is a tail, power law tail, which decreases quite slowly. Second, the contact times some constant h bar squared over 4 pi m is equal to the derivative of the energy. So it's always energy per unit volume with respect to minus 1 over scattering length. So this is sometimes called adiabatic relation, because you have to change the scattering length and keeping fixed the entropy density, and also keeping fixed the number densities n up and n down. And then, okay, as usual in thermodynamics, you can change ensemble. So this is basically the microcanonical ensemble, but you can also work in the canonical ensemble. So in this case, you have to put the free energy here. And instead of keeping fixed the entropy, you should keep fixed the temperature. And always, and again, the density fixed. Or you can also work in the grand canonical ensemble. And in this case, what you have here is the pressure, because pressure is the grand potential per unit volume with a minus sign. So therefore, you have here 1 over A without the minus sign. And now you should keep fixed the temperature and the chemical potentials. Voilà. The third relation is about the G2 function, the density correlation function, at short distance. When R goes to 0, this will behave like a contact divided by R squared. So it diverges. And it turns out there is a factor 1 over 4 pi squared. And the last relation is the one which maybe is the most surprising at first sight. So it tells you that the total energy per unit volume is given by the following expression. Sum over sigma equal up or down, integral over momentum, d3k over 2 pi cube, h bar squared k squared over 2m times n sigma of k. So if I would stop here, that's just the kinetic energy. The kinetic energy actually is divergent because of this tail. So you have 1 over k4 times k squared from the Jacobian, so it's divergent. But if you subtract this tail, minus c over k4, then you get something finite. And this is basically the total energy. There is just one additional term, which is contact over scattering length times some constant, which turns out to be h bar squared over 4 pi m. And that's it. So these are the basic 10 relations. So C is often people define it from the tail. So in the following, actually, I will rather use the second relation here as a definition of C, and I will derive this one. No, because I mean the concept of contact, it just arises from these relations. So to get some intuitive understanding of what is the contact, maybe the best thing is to look at this relation and to realize that it implies the following. So imagine that you measure all the particle positions in your gas. So you have your single atom imaging and everything. You measure all the positions of all the particles, let's say in a unit volume. Then you look, do I have some pairs of particles which are very close to each other? Let's say that where the distance between the two particles is smaller than some epsilon. Okay? So you count how many pairs do I have in my image where you have two particles at distance smaller than epsilon. Okay? Then the number of such pairs will be just given by the contact. It will be proportional to the contact times epsilon. And okay, it turns out there is 1 over 4 pi here. So you see that the contact, it controls the probability to have two particles close to each other. Moreover, note that this epsilon here is actually anomalously large. I mean, of course it's small because epsilon is small, but it's much larger than what you would usually have, because usually you would have epsilon cubed. Okay, if you have particles which are not correlated, or let's say correlated in a non-singular way, then the probability to have them a distance smaller than epsilon in 3 dimensions, it will scale as epsilon cubed. So here it scales as epsilon. And of course, this is just a consequence of this divergence of the density-density correlation function. Okay, so of course there are experiments, in particular in the group of Debi-Jin and Gila, where they measured the momentum distribution by doing time of flight and switching off the interaction at the same time then switching off the trap. There are also experiments in the Paris group at ENS, where they measured the equation of state and then took a derivative of the data to get the contact. And then the most accurate measurements of the contact are actually done by Bragg spectroscopy in the group of Chris Vail and Swinburne, where they look at the large momentum tail of the static structure factor, which is nothing else than the Fourier transform of the G2 function. So basically they look at this thing, but in momentum space. Okay, so now I would like, as I advertised, I would like to give you a simple derivations of these relations. I mean, it will be simple, but still there is a bit of tricks to do, because, and this is related to the fact that we cannot just say that we have a Dirac delta interaction. So somehow we have to do what is sometimes called the UV regularization, or in more pedestrian terms, we have to start with some finite range, which will give us some cutoff, and then we should send the cutoff to infinity. So in my opinion, the most clean and simple way to do that is to work with a lattice model. And I will denote it by LM. So, which means that what we do now, instead of working in continuous space with a finite range, as I was considering before, now we will discretize the space. So we will imagine that our atoms, instead of living in the continuous space, they live on a lattice. But of course, the lattice spacing that I will call B here should be sent to 0 at some point. So, to be precise, I will start also in a finite volume, in a finite box of linear size L. And therefore, the positions of the particles will belong to the following set. So the coordinates should be B times the integer, and we are in 3D. And of course, they should be inside the box, so they should be in 0L cubed. And this set I will denote it by calligraphic R. And now for the interactions between the fermions in our lattice model, we will just take the simplest interaction, namely on-site interaction, like in the Hubbard model, actually. So we will take an interaction V of R1, R2, which is just a Kronecker delta of R1, R2. So the particles interact if they are on the same side. And so, of course, we need to put here some prefactor that I will call G0. And also, it will be convenient to divide this thing by B cubed, so that this Kronecker delta divided by B cubed is a sort of Dirac delta discretized. But I mean, this is just a matter of convention, of course. So the statement of the universal zero range limit, of course, remains the same as before. So in this case, it just means that the lattice model will converge to the zero range model in the limit where B goes to 0. So B now here is the lattice spacing, but you see that it also plays the role of the range because we have on-site interactions. And again, of course, we should keep the scattering length fixed. So now let me write down the Hamiltonian of the lattice model. And it's maybe a bit more convenient to write it in second quantization, so that's what I will do. So it's the sum over spin, sigma equal up and down. And then you have to sum over momenta. So the momenta, to be accurate, they have to belong to a set that I will call DL. And DL here is simply the following. So since we are in the box, the momenta coordinate should be 2 pi over L times some integer, positive or negative integer, with 3 coordinates. And it should also be inside the first Brillouin zone of our lattice that I will denote by D. So D here is the first Brillouin zone, so it's minus pi over B, pi over B. So here we have to sum over all k in this set, and then we have h bar squared k squared over 2m, and then as usual we have c dagger k sigma c k sigma, So these are the creation and annihilation operators in the plane wave on the lattice. And then, so this is just like Joseph earlier today. And then we have the interaction term. So, and unlike Joseph, I will keep it in the position space because it's simpler. So it's the sum over all positions R belonging to the set calligraphic R. There is a B cube here. So, I mean, it turns out there is a B cube because you see that in this way, this is kind of an integral which is discretized on the lattice. And then there is, we have on-site interactions, so we have n up of R, n down of R. Of course, as we discussed this morning, if you prefer, you can put this in normal order, but you don't need to. So, of course, here these density operators, they are equal to psi, dagger, psi. And these field operators, they satisfy anti-commutation relations. So there is a little subtlety because we are on the lattice here. You know, in the anti-commutation relation, instead of Dirac delta, you have a discretized delta. And of course, these guys are just the Fourier transforms of these guys. So now there is a little exercise to do, and I will not do it now here. But you have to solve the two-body problem on the lattice. So you have to look for the scattering, two-body scattering states on the lattice. So if you are interested how to do it, I mean, a quite simple way to do it is to use the T matrix, and this is basically what Mira will describe, I think, this afternoon or tomorrow, even though she doesn't want to use the lattice model, but basically the formulas are the same. And or if you want to see it for the lattice model, you can look in my paper with Yvon. So anyway, this is quite straightforward, and what you find is the following. So it's 1 over G0 equal to m over 4 pi h bar squared a minus integral over the first Brillouin zone d3k over 2 pi cube m over h bar squared k squared. So this is what you get if you solve the scattering problem on the lattice. You calculate the scattering length A for a given G0. Remember, G0 is just the strength of your on-site interaction. So, so that's what you get, and I will comment on it in a second. But first, let me also mention that if you calculate this zero energy state, phi 0, then you find the following thing, which will be useful for us. It's that phi 0, if you take r equal to 0, so on site, it's equal to minus 1 over G0 times some constant, which turns out to be 4 pi h bar squared over m. Okay, so now let me comment on this relation. So remember, we are interested in the limit when b goes to 0, when we go to the continuous space, and at the same time to the zero range interaction. So you see that in this limit, the Brillouin zone here grows, okay? So when b goes to 0, the Brillouin zone here grows, and therefore this integral actually will diverge, because we have the Jacobian here, k squared dk divided by k squared. So this integral will diverge like 1 over b, some constant over b. So you see that 1 over G0 scales like a negative constant times 1 over b, or in other words, G0 scales like a negative constant times b. And this is not surprising, because you see here, if G0 would just be a constant, then here we would have something which approaches a Dirac delta. But as I already explained, this is not what we want. In fact, you remember from the square well that what we want is something like a Dirac delta multiplied by b, because the depth of the square well should be 1 over b squared instead of 1 over b cubed. And that's precisely what we get here. This g0 here scales like b, so that in the end we have something like 1 over b squared. So that should not surprise us. Okay, so now to the derivation. So as I already said, I will use this thing as my definition of the contact. So I will say that the contact times this constant h bar squared over 4 pi m is by definition equal to the derivative of the free energy with respect to minus 1 over a. I will work in the canonical ensemble, but I mean that's just it doesn't matter, of course. So at constant temperature, constant number of spin up and spin down, and constant volume now. So I'm at a finite volume so far. Okay, and now I take this as a definition, and I would like to derive this, and this. So for this, actually it's very simple. There is just one key point, which is to realize to use the Hellman-Fineman theorem. Okay, so the Hellman-Fineman theorem, it tells you that, for example, here, if you are in the canonical ensemble, then the derivative of the free energy with respect to whatever parameter of your Hamiltonian is just equal to the expectation value of the derivative of your Hamiltonian with respect to this parameter. I mean, usually you write down the Hellman-Fineman theorem for some eigenstate of your Hamiltonian, but then if you perform the thermal average with a Gibbs distribution, you can easily show that you have this relation, which is also pretty well known. This is the free energy, yeah. Yeah. Okay, so now, of course, here we derive with respect to the scattering length, and in the Hamiltonian, what we have here is rather G0. But we know that G0 is directly related to the scattering length through this relation. And this here, for us, at this point, is just a constant, because so far we are working at a fixed lattice spacing B. So therefore, you can say that d by d minus 1 over a is d by d 1 over g0 times, d 1 over g0 by d 1 over a. Okay, so you just do this chain rule, and you very easily arrive at the expression that this is equal to the interaction energy divided by G0. Sorry, actually, okay, I went slightly too fast. So let me add back one step. So it's minus G0 squared, expectation value of dH dG0. And then there is a constant, which is this one, m over 4 pi h bar squared. Okay, and now this thing here, so you see that you take the derivative of the Hamiltonian with respect to this guy, so what you get is just this thing, and this is nothing else than the interaction energy divided by G0. Interaction energy is expectation value of this. Okay, so this is just interaction energy divided by little G0. And basically that's the main steps. The rest is just crank, the stuff, and we will get the tan relations. So so let me just slightly rewrite this relation. So here now we have shown that the contact is equal to the interaction energy times some stuff. So I will write it the other way around and say that the interaction energy is equal to the contact times some stuff, which turns out to be 1 over G0 times h bar 4 over m squared. So now, actually, what I will do, I will first derive this relation, the energy, which is called sometimes the energy relation. So the total energy is, of course, just the kinetic energy plus the interaction energy. And now, in fact, we are almost there. Because, so let me already now divide by the volume. So replace E by calligraphic E and take the thermodynamic limit. But this is just, if you want, you can take the thermodynamic limit slightly later, it doesn't matter. So the kinetic energy is the sum over sigma equal up and down, integral over the first Brillouin zone, d3k over 2 pi cube. I mean, it's the expectation value of this thing, right? And I took the thermodynamic limit, so therefore, instead of a sum over k here, I have an integral over the Brillouin zone. And then here I have h bar squared, k squared over 2m, and I have n sigma of k. Okay. So now for the interaction energy, I'll just use this relation. So I'll say that the interaction energy is the contact times 1 over G0. And then I will do something which looks a bit weird at first sight. So I will replace 1 over the G0 by all of this stuff. And basically that will give me this relation. Because you see that if I replace 1 over G0 by this integral here, first of all, then I will get here actually minus c over k4. You can easily check that the factors are correct. Basically, it's k squared divided by k4, which indeed corresponds to this k squared here. And then, of course, there is this other term here, which you have to multiply again by the contact. So that's how you get this term here, c over a times this stuff here. Okay, so now we are almost there. All we need to do now is to take the zero range limit. So we need to send the range to 0 in order to get the zero range model in order to arrive here. But here it's very easy, because you see that when you send the range to 0, as I already mentioned, what happens is that the Brillouin zone fills the entire space. So instead of the Brillouin zone here, you get the entire space R cube. And that's it. You get this relation. Any question? They are simply related to each other by this equation. That's all. So the derivative. What? It's a constant. The second term is a constant. So here we are changing the scattering length, but keeping fixed our lattice. So keeping fixed B. So keeping fixed this stuff. Voilà. Okay. So now that we have this relation, it immediately follows that we have the first one, because you see that this integral apparently converges. And so in order for this integral to converge, you must have this thing. I mean, this integrand has to go to 0 at infinity. If you exclude some very weird unphysical situations, then this is what should happen. Okay? So we have this relation. And now for this relation with the G2, I have some derivation which is basically, you can see it in the notes. It's based on the thing that I already used in this hand-waving derivation of the zero range model, namely that the many-body wave function will behave like phi 0 of Rij times some capital A of the rest when the two particles are close to each other. And this, of course, we expect that it holds also for the lattice model. Okay, it's also possible to derive this connection 1, 3, so this connection between n of k and G2 of R. It's also possible to derive it directly from the zero range model. And this you can find in my paper with Yvon. But let me mention the basic idea because it's very simple. So the idea is that the many-body wave function, because of the contact condition, it diverges like 1 over R at short distance. So this immediately implies that the G2 function has to diverge like 1 over R squared. And on the other hand, if you take the Fourier transform of 1 over R, you get actually 1 over k squared. So if you have a function which diverges like this at small r, then its Fourier transform will have a 1 over k squared tail at large k. And then you take the modulo squared, and you get the 1 over k4 tail of the momentum distribution. So, and this also tells us a bit about the physical interpretation of the contact. So, as I already mentioned, it measures how many particles do we have which are very close to each other. But you can also imagine that when these particles are close to each other, they also have a very large momentum. In fact, they have a very large and opposite momenta, plus k and minus k. And this is why it gives rise to this tail. Questions? Yeah. I don't get the question. No, not quite. I mean, there is some work to do because you can do a Fourier transform. Here I was bullshitting a little bit. Okay, so you can do a Fourier transform of the wave function. Okay, but then in order to get the momentum distribution, you need to integrate over the other coordinates and take the modulo squared and integrate. And same story for G2, you need to take modulo squared and integrate. So that's a little exercise that you can find in my paper with Yvon, but it's not a big deal. I mean, in fact, it's slightly tricky because this Fourier transform actually, it's in the sense of distributions, but who cares? Okay, so so in fact, I had the last chapter, but I was already guessing that I might run out of time. So so what I will do, maybe I will just briefly in the remaining 5 minutes explain what's the idea of this last chapter, and again you can find it in the notes if you're interested. So so the last chapter was supposed to be about the two-channel model. Okay, so what is a two-channel model? It's in fact it's a family of models, but it's the simplest way to write down a model which takes into account a bit the microscopics of the Feshbach resonance. So in a two-channel model, you say the following: I have my atoms, which are fermions, spin up or spin down, but I also have a molecule, which is the closed channel molecule that Jörg told you about, which is of course a boson. And then I can have processes where my two atoms are converted into a molecule and other way around. Basically, that's all there is to a two-channel model. And okay, technically you have to do again some ultraviolet regularization. So in these notes I did my favorite one, which is to put it on a lattice. And now so if you want, you can solve the two-body problem for such a two-channel model. And if you assume that the energy of your closed channel molecule at rest, because of course it has an energy offset, EB, which depends on the magnetic field. Okay, the B here is not the lattice spacing, but it means that this is the bare closed channel molecule, bare without the coupling to the open channel. So, so then usually people assume that this is a linear function of the magnetic field with some magnetic moment here. And then if you solve the two-body problem, you get this celebrated formula, you know, for that scattering length as a function of magnetic field is given by this expression. So, you know, it has this divergence at some Feshbach resonance position B0. And now I would like to make 2 points. So first of all, the universality that we discussed in the beginning is, of course, is also expected to hold for a two-channel model. So meaning that if you take a two-channel model, it has to approach the zero-range model in the limit where. And now it becomes slightly more complicated, but maybe also more interesting for experimentalists, because what you find is that if you just look at the two-body problem, because that's what you can do easily, you will see that your two-channel model indeed approaches the zero-range model under the following conditions. So first of all, of course, your range B, which in my case is again the lattice spacing, of course it has to be much smaller than other length scales in the problem. So scattering length, interparticle distance, 1 over kf, and also the thermal wavelength, of course, if you are in a gas. But actually you find some additional conditions which you'd better check whether they are valid in your experiment before you claim that you have universal results. So first of all, you have that this length called capital R star also has to be much smaller than these guys. I don't know if anybody introduced capital R star before. Anyway, it has a simple expression you can find in the notes, and basically it's the effective range. I mean, it turns out that it's proportional to the effective range. And then there is another quantity which also needs to be small, and this was a bit of a surprise to us. Namely, you find that the geometric mean of this R star and the background scattering length also need to be small. Okay, background scattering length is actually the scattering length that you have far from the resonance. And this is the background scattering length. Okay, and my last point is that of course, if you have a two-channel model, a natural question to ask is what if I measure how many of these closed channel molecules I have in my system? Okay, so by the way, this is a little bit a tricky story, because as I mentioned, these are just bare molecules, so already at the two-body level, in fact, what you have is always a superposition, a coherent superposition of a closed channel molecule and two atoms in the open channel. But anyway, in quantum mechanics, we can define an operator which counts the number of these closed channel molecules, and we can ask what is its expectation value. And actually, this is also accessible experimentally. So in an experiment that was done quite a long time ago by Randy Hewlett, they were just exciting, so using a laser with a well-chosen frequency, they were just exciting the transition from the closed channel molecule to some electronically excited state, which then decays. So then you can quite easily show that if you do that, you will lose atoms at a rate which is proportional to this number of closed channel molecules, right? Because each time you have a closed channel molecule that you excite and then it's de-excited and leaves the trap, then you basically lose 2 atoms. Okay, so and what we showed, and in fact it's very, very easy to show, is that actually this thing is just equal to the contact times some factor, some constant that you can easily calculate. And the reason, and I will finish with that, the reason that is again very simple. I mean, it's even simpler than this story of the 10 relations. it just follows very directly from the Hellman-Fineman theorem. And the reason is that in the two-channel Hamiltonian, if you ask what depends on the magnetic field, actually this is the only thing which depends on the magnetic field. It's the energy offset of the closed channel molecule. All the rest is independent of the magnetic field. And therefore, if you take your two-channel Hamiltonian, you take derivative with respect to the magnetic field. Then this is nothing else than the number of closed channel molecules times this magnetic moment. And then, of course, this thing, again, I can play the similar game than before, because B is simply related to the scattering length. So I can say that this is the derivative with respect to 1 over A times stuff. And so this is the contact times stuff. That's it. Thanks. Let's go for lunch. Oh, Joseph. Oh, let's go for the picture then. But you had a question?